data analysis, its applications in molecular simulations. So it's okay with you, Doctor. You can start.
Awesome. Thank you. And yeah, I'm actually almost a doctor, so I'm a 5th-year graduate student, so almost there. But thank you. I appreciate the confidence in that it will happen.
It's okay.
Yeah, so as I stated previously, I'm going to be talking about some applications of topological data analysis, molecular simulation, and I also added in a bit more on some soft matter systems that we're looking into that I thought might be of interest to this audience. So again, I'm a 5th-year graduate student in the group of Victor Zavala in the Chemical and Biological Engineering Department at UW-Madison. And so this is in collaboration with a lot of experimentalists and simulation experts. So that's what the focus of this talk will be on. So for those of you who maybe are unfamiliar with this idea of liquid crystals essentially represent a state of matter that has characteristics of both a liquid and a solid. So what we're looking at here on the left-hand side basically is a molecule known as 5Cb, which I'm going to represent as this sort of blue ellipse. And 5Cb can take on different states, right? So it can form sort of an isotropic liquid where there's really not much long-range ordering in the system. It could form a crystalline solid where there's a tremendous amount of long-range ordering, right? And it can also take on a state of matter that's sort of in between the two. So what you can think of a liquid crystal as is something that maybe flows. And so what's really nice about these systems is that we can leverage these liquid crystal systems to sort of understand and create what we call liquid crystal sensors. And so on the right-hand side, we're seeing a liquid crystal sensor, an animation of one, where what we have is a thin film of liquid crystal that's sort of deposited on a reactive surface. And so the liquid crystals, again, are represented as these ellipses. And this liquid crystal system will interact with this surface. And these liquid crystals at the beginning, when it's not exposed to an analyte, will be homeotropically anchored. So they're sort of standing on their heads on top of this surface. And the reason they're doing that is because these liquid crystals are sort of interacting with these reactive sites on this surface. And so what will happen is we'll expose this sensor to a gaseous analyte, which we're representing by these sort of yellow balls. That gaseous analyte will diffuse to the liquid crystal and bind to these binding sites. And so when it does that, it actually changes the orientation of these liquid crystal systems. And what's interesting about this change, right, is that we actually see and induce sort of an optical response when we see this transformation. And so here are some experimental images of liquid crystal sensors. And so on the very left-hand side, what you're seeing is sort of the state of the liquid crystal sensor before it's been exposed to any sort of analyte, right? And so on the left-hand side, what we're looking at is basically an image where we have looking at the sensor or the sample through a cross-polarized microscope. So the way that this works is essentially we feed light through a polarizer. That light is completely polarized. And if that light is not bent or refracted in any way, there's another polarizer that's above that first polarizer that's orthogonal to that first one that will completely block the light. So when the liquid crystals are in this homeotropic anchoring state where they're sort of standing on their heads, they don't bend or refract the light. And so we end up just seeing sort of a black image. Now what happens is we expose this system to a given analyte, and those liquid crystals, as I showed before, start to change their position, right? They start becoming what we call planar anchored. And when that happens now, because these liquid crystals have sort of these, crystalline properties, they start to bend and refract the light around that second polarizer. So what we're seeing here on the left, right, is again where we start at before we expose the system. And then once we expose the system, right, these liquid crystals start to reorient, and we get these very, very interesting colors and textures that start to show up. And so, we expose the sensor to a system, and then at the end of the transformation, we get these really cool textures. And one of the important aspects of these systems, right, is that they're very, very sensitive. And so one of the things that we want to ensure with these sensors is that, if we're detecting something, let's say chlorine or hydrogen sulfide or something like that, right, we want to be able to tell if, that level of chlorine is dangerous for humans or if it's an acceptable level, right? So we have the sensor response. We want to be able to not only tell whether or not it's there, we want to see at what level that concentration is. And so here we're looking at two systems where we have a low analyte concentration and then a texture associated with that on the bottom, and then a higher analyte concentration. And so our goal here is really to quantify the differences between these endpoints. And the way that we're going to do that is through this idea of topology. So again, here on the left-hand side, we have our low analyte concentration systems, and we have these given textures. And remember, this is just, we're looking at the textures of these liquid crystals from like sort of a macroscopic view. And then on the right-hand side, we have our liquid crystal textures where we have our high analyte concentration. And again, our goal here is to quantify the topological differences between the endpoints of these sensor responses. So sort of bin them as, low analyte or high analyte concentration. And so many of you may already know this, but I'm going to go through it for maybe those of you who aren't as familiar. This idea of measuring the topology of an image. And so what we're going to do is we have our image here on the left-hand side. And what we're going to do is we're going to treat that image really as a manifold with an associated function, right? And so here we still have our two spatial dimensions, our x and y dimensions, but now we're considering this function as sort of sitting on top of this manifold, right? And so here what we have now is this function is sort of represented by the pixel values that we're looking at in our images. Now, what's nice about this representation is that we can sort of quantify the topology of this manifold at various function thresholds. So what we're going to do is we can imagine our threshold as being this sort of flat plane that we see on the left-hand side. And I'm going to pass that flat plane from the bottom to the top of this system. And so what's happening is as I pass that plane up, right, I'm going to add more and more of this sort of manifold into my system. And eventually I'm going to start, sort of slicing off the local minima of my system. And then eventually I'll come back and have like a full picture of my manifold. And the way that we're going to sort of quantify the topology of this image is by at each one of these function thresholds that we design, we're going to measure something known as the Euler characteristic. And now the Euler characteristic, right, as many of you know, is just a simple topological invariant that sort of measures the number of connected components and just subtracts the number of holes and gives us a single value for that system. So now what we're going to do, right, is we have our filtration. We sort of understand what that is. And what we're going to do is we're now going to construct something known as an Euler characteristic curve that we're constructing by measuring the topology at these different filtration levels, right? And so again, we have our filtration here on the left. And on the right, I'm kind of showing you what those different filtration function, those thresholds look like, and then also what the associated Euler characteristic is for these systems. And so on the right-hand side, we can see that when we start off at a low filtration value, like 0.1, we're sort of slicing off the local minimum of this function, right? So we end up with a bunch of little connected components. And so we're getting a more positive value. As we keep going through, we slice off more and more of these local minima of this function, and we end up with more and more connected components. And so what that does is it sort of drives our Euler characteristic value to be more positive. Now, as we keep going through this filtration, right, these connected components start to become connected to each other via things like saddle points on this surface. And so as we start to connect those, right, we start to form cycles or holes in this image. And so what we're seeing now is we've got really just a single connected component, but it has many, many holes. And so what that does is it sort of drives our Euler characteristic negative again. And then as we keep going through, right, the local maxima of our system now start to fill in these different holes of our function. And so eventually, as we keep going and we start adding more and more of those local maxima in, we come back to our original system, which is now just a single connected component. So through this, what we're doing really is sort of quantifying the topology of this image at these different threshold levels and encoding it in this representation known as the Euler characteristic curve. So again, pointing back to our problem, right, we had these sensors that we're trying to distinguish between low concentration sensors and high concentration sensors. And so here's sort of a subset of those images where we're looking at low concentration, and then a subset where we're looking at high concentration. And on the right-hand side of this slide, what we're looking at is basically the average Euler characteristic for these two systems, for all this data. And what's nice, right, is that you obviously see that by just looking at the averages, right, there's a dramatic difference in the Euler characteristic curve for the low concentration systems versus the high concentration systems, right? And what this sort of foreshadows is that we're actually able to classify these sets of images with 95% accuracy using just a simple linear classifier. And what's really interesting is that to get this same level of accuracy previously, we required these more complex convolutional neural networks to obtain this level of accuracy. So here we've sort of been able to optimally represent this image via the Euler characteristic curve and its topology, and then simplify the model needed to obtain this classification accuracy and sort of throw away the more complex CNN. Now, just to show you that this isn't sort of a trivial result, right? What I'm going to do is I'm going to compare sort of a low dimensional representation that we obtained from the Euler characteristic curve versus the 2D Fourier transform of the system. And so on the left-hand side, what we're doing is we're taking our Euler characteristic curves, which are essentially a vector of numbers, right? We're going to stack those vectors into a big matrix and perform PCA on that matrix. We're going to do the same thing with the Fourier transform, but taking the coefficients of that Fourier transform, stacking it into a big vector, performing PCA. And what we see on the left-hand side, right, is that the Euler characteristic curve, using only the first two principal components, already shows really a great sort of separation in the data, right? You can imagine I could draw sort of a vertical line at 0 here and get a pretty good classification with just these two components. If I look at the Fourier transform, right, I really don't see that same sort of separation. And again, what this foreshadows is that when we try to do this classification using the Fourier transform and the linear classifier, we find that the classification rate is actually quite poor. So the Euler characteristic curve in this case captures information that this Fourier transform is sort of missing. So, okay, so now I'm going to hop into some of these ideas around molecular simulation. And the thing on the right is supposed to be an animation. I hope you can see it as an animated, but basically the molecules are sort of bouncing around really quickly. And so the system that we're looking at here is something known as a self-assembled monolayer. And the thing that we're trying to understand in these simulations for these self-assembled monolayers is something known as hydration-free energy, or HFE. And so really the idea behind this is that on the left-hand side, where we have like sort of a snapshot of our simulation, and in this simulation, we create sort of a probe volume, right? And in this probe volume, we sort of bias the molecules that enter the volume to sort of leave the volume, right? And the goal here really is to sort of sample the probability that this volume will contain X number of molecules, right? So we're trying to construct sort of a probability distribution and understand, you know, what's the probability that there are 10, 20, 30, 50, 100 molecules in the system. And understanding that probability allows us to really accurately compute these ideas of hydration-free energy. But as you can see on the right, these simulations are very packed with water, right? Because we're sort of simulating this self-assembled monolayer against a bulk interface of water. And so the probability that, you know, this large volume is going to be, you know, going to contain almost 0 molecules is going to be very, very low. So in order to obtain that information, right, we have to do these really computationally expensive sampling methods, right, where we sort of run these simulations for really long times to be able to get a sampling of these low probability events. And so that's sort of a bottleneck in understanding or quantifying the hydration-free energy of these systems. And so really our goal here is to sort of rapidly estimate this hydration-free energy without this expensive sampling method. And so the way that we're going to do that is really by understanding something known as the interfacial water layer of these systems, right? So on the left-hand side, we have our, our SAM, right, or our self-assembled monolayer, which we're seeing on the bottom. And then above it is the bulk water. And what we're going to be looking at is this sort of little slice that's next to the SAM, or self-assembled monolayer, that's known as the interfacial water layer. And the reason we're looking at this is because there's a lot of theory around understanding the hydration-free energy of these systems. And a lot of them point to this idea that there are interesting temporal and spatial fluctuations in the water at this interfacial layer that sort of hint at what the hydration-free energy of this system might be. And so here we're sort of looking at a side shot of that SAM simulation. We have our interfacial water layer that we're sort of slicing out of the simulation. And then in the center, we're looking at sort of a top-down shot of that SAM water, or that interfacial water layer, right? And what we're doing is we're taking these water positions, and because we have this thing over time, we're going to sort of time average these water positions into sort of like a density field, right? To understand, how the water is behaving in this process. And so again, here we're showing, the different density fields for these systems. And we're also showing, the different hydration free energies that we're looking at in these systems. And so what we've done here is we've taken these simulations that we've computed the hydration free energy for using these really, very long time sampling methods. So we can get this accurate hydration free energy. And then we're associating with it these sort of density fields that we're getting over very short periods of time, right? So we can obtain these density fields very rapidly. And again, the goal here, right, is to rapidly predict this hydration free energy just using this water density field rather than the very computationally expensive sampling process. And what you can see, right, is that, obviously this is somewhat of a difficult problem because when we look at low hydration free energy to high hydration free energy, we're not seeing a tremendous amount of difference in these fields. But again, the way that we can approach this is similar to the way that we approach these LC textures, these liquid crystal textures that we were looking at, right? We can again represent this as sort of a manifold with an associated function, right? And perform our transformation where we do our filtration, we can obtain our Euler characteristic curve for these water density fields in the exact same way that we did it for the images. So again, now here we're looking at the left-hand side, our hydration free energies, right? And now even when we just look at it in this way, right, we can see that now there are starting to be some interesting differences in how these fields are behaving when we change the hydration free energy from 30 to 60 to 100, right? And what's also interesting, right, is that when we look at the right, at the Euler characteristic curves for these different systems, we can see that there's almost a smooth transition, right, from this low hydration free energy at 33 and then to 60 and then to 100. And so we're sort of seeing that there's, these topological differences between these different fields that we're sort of capturing with the Euler characteristic, and that sort of almost smoothly varies with the hydration free energy for each of these systems. And so what we've noticed also about these topological descriptors, and that's really important for the analysis of these molecular simulations, is that the topology is really stable when characterizing these systems, right? So for example, I have a simulation that I'm running for a period of time, and I want to sort of subsample that simulation to gain more data from it, right? And if I don't want to, sample the simulation at the beginning of the simulation versus at the end, after the system is already equilibrated, and get a dramatically different result in the way that I'm sort of measuring or quantifying these systems. And so what's interesting, right, is that, here we have different time slots where we've sort of averaged, between 0 and 200, 200, 400, 400, 600, et cetera. And what we can see is that while the density fields look different, right, the Euler characteristic curve is almost identical for each of these systems. So again, what we're seeing, right, is that the density fields change over time, but the topology measured via the Euler characteristic really remains a sort of stable measure or quantification of these systems. So again, what this is all leading up to is this idea of rapidly predicting the hydration free energy for these systems. And so what we're doing here is we're taking as input our Euler characteristic curves, right? And we have a set of simulations where we've computed, right, the hydration free energy via this long time sampling process. And so what we're doing is we're taking that data and we're sort of training a linear regression model to predict the hydration free energy for those systems. And so what we're seeing on the right here is a completely separate set of simulations where we've again computed the Euler characteristic via these density fields using a short time period of the simulation. And then we're predicting that hydration free energy that's been verified by these long time sampling methods. And what you can see is, right, is that the accuracy is incredibly high, even using simple linear regression. And again, sort of the trend that you'll see in this talk is that for these methods and to get this same level of accuracy, we previously required complex two-dimensional convolutional neural networks, right? So again, this optimal representation of the data via the Euler characteristic and topology is able to allow us to rapidly predict these hydration free energies without the need for these really complex, uninterpretable convolutional neural networks. And again here, to just show that this isn't a trivial problem, right? Again, what we're doing is we're doing our principal component analysis on the right or on the left, where we're using our Euler characteristic curves as sort of vectors, right? Stacking those into a matrix, performing PCA, and the same with the right, just like we did for the images where we do the 2D Fourier transform, take the coefficients and perform PCA. And again, what we're seeing on the left, right, is that the Euler characteristic curve is really able to capture this sort of data manifold, right? So if we look here on the very left, we see we start at low hydration free energies. Then as we sort of follow this curve, right, we get higher and higher hydration free energies. When we look at the Fourier transform, right, we can see that there's maybe some structure in there, but there isn't a tremendous amount of structure, right? Not nearly as coherent as we're seeing on the left with the Euler characteristic curve. So again, the Euler characteristic curve is really capturing data that this Fourier transform is missing. And previously, again, just to reiterate, right, we needed these more complex convolutional neural network models to be able to obtain the same level of accuracy. Okay, so now what we're going to do is we're going to move into another molecular simulation, but in this time, we're going to be looking at higher dimensions. And I know many of you are probably familiar with much higher dimensions than 3, but here we're just going to move from 2 to 3. And so what we're looking at here on the left-hand side is, again, this is supposed to be a movie, so it should be animated. Basically, what we're looking at is a reactant, which is sort of centered in this simulation. And then what we're looking at is that reactant is sort of solvated in a co-solvent and water mixture. And now what's really interesting about systems like this, so here what we're looking at is what's called an acid catalyzed reaction. And so the goal here is to turn things like fructose and other, sort of simple sugars and things that you can get from biomass into things that you could make, like, for example, polymers out of, right? And so an important step in that is this sort of acid catalyzed reaction step. And what's really interesting, right, is that here we have our reactant in the center. And when we look at experiments right here on the right-hand side, if you follow for particular molecules, red to green to blue to black, all we're doing is increasing the co-solvent concentration by weight and removing water from the system. And this is really interesting because this central molecule is really reacting with the water. So it's kind of bizarre that you remove water and you get an increase in the reactivity, right? But the theory here is that actually the structure of water in the simulation and near this central molecule is actually being changed by the co-solvent. So the idea is that as the co-solvent is added more and more, that water becomes concentrated at particular areas of this molecule that allow it to react more frequently. And so what we're trying to do here really is sort of understand how water structure changes and it impacts the chemical reactivity of this reactant. And so something that we found really nice about these topological methods, right, and the Euler characteristic and things like that, is that these methodologies generalize to higher dimensions, right? We can do the exact same thing that we did in 2D to 3D without really changing the mathematics very much. And so again, here we have, from our SAM systems, these atomistic simulations, and then we have our water densities, which are on the bottom. And then here we're transitioning to a 3-dimensional system, right? So again, we have our reactant, our co-solvent, and then we're going to have water that's sort of mixed in there, and we're going to just sort of let that water sort of freely move around this central molecule. And so what we end up seeing, right, is these interesting water density fields. So now we've gone from this sort of 2-dimensional water density to a 3-dimensional water density. And we're going to process that via the Euler characteristic curve again. So, right, again, here, just a reminder of what the data looks like, right? Again, this simulation, and we have our water density field. And so now what we're going to be doing is the Euler characteristic curve, but in this case, right, it's not easy to visualize the transformation, right? In the 2D system, we could draw it, we could sort of move the manifold into 3D and sort of show this filtration passing through, right? So in this case, we would probably need like a 4D plane passing through a 3-dimensional system, and I have no good way of visualizing that. So the idea here, right, is the same as we had done with the images, right? But now we're just going to consider, the density levels in this particular case, right? So what we're doing is we're starting at low density areas of this density field, and we're going to sort of add those into our resulting structure that we're measuring. And then as we keep going through this filtration, right, we're going to start adding more and more information and more structure to the sort of the 3-dimensional system that we're measuring the topology of. And so what we start to see, right, is when we start out at these low density levels, right, we get a lot of connected components in our system. So we start, from no connected components to a positive number of connected components and few holes, right? So basically we're seeing a positive value here. As we keep filling up this system, right, we start to form holes, or in this case, they would be considered handles for this process, right? And so we start to get a negative value. So now it starts to become dominated by these holes. Now what happens eventually, right, as many of you are familiar with probably, is these holes may become encapsulated inside the surface that we're measuring in that structure, and we end up with voids, right? So voids are another interesting topological characteristic that we consider in the Euler characteristic. And so the Euler characteristic shifts from just connected components minus holes to connected components minus holes plus voids. And so that's why we're seeing, this first peak, that second value, and then a third peak here, which accounts for the voids in our system, right? And as we keep going through, eventually those voids are filled, and we end up back with just a single connected component. And so again, we're going to use this Euler characteristic curve to sort of quantify these water densities in their topology, and we're going to try and use this information to predict the reactivity of this reactant. So again, I just want to reiterate on this really important point, and something that we've, experienced in these analyses, is that again, topology is very stable, right, when we measure these systems. So again, here on the left, we're doing an average from 0 to 200, 200 to 400, et cetera, just like we had done with the MD simulations for the two-dimensional system, right? And so what we're seeing here right now is that these density fields are now dramatically changing. We're seeing a lot of differences in these fields, and it would be hard for me to say that, all of these systems belong to the same family or the same simulation. But when we look at the Euler characteristic curves, right, there are some slight differences, but we're not really seeing a dramatic change in the structure or the values of these Euler characteristic curves. So again, this density is changing over time, but the topology of these systems is really remaining very stable. So again, here what we're doing, right, is our goal is to sort of understand the connections between the topology of this water structure, this density, and whether or not we can use it to predict the associated reactivity increase for this central molecule. And so here we have our inputs on the left, which are Euler characteristic curves, which we can consider just as a simple vector. We're going to train a model on a set of simulations and a set of chemistries, right? So here we look at a different set of chemistries in the training set than we do on the testing set, right? So here I've trained it on a set of chemistries and, different water percent weights and different central molecules. And our goal is to predict a completely different set of chemistries on the right-hand side, right? And so what we find is that using just linear regression and the structure of water in these simulations, we're actually able to really understand and predict the reactivity for these systems. And again, what we're predicting here isn't, a simulated value. We're predicting actual experimentally verified values. So scientists have gone out and verified these reactivity increases in the lab, and we've been able to predict them using this sort of simple model. And, again, sort of the thread through all of this, right, is that this previously required much more complex three-dimensional CNNs, right? So these things can have hundreds of thousands of parameters and, are highly uninterpretable. And so we've reduced that really to only 30 parameters in a linear regression model. And we're able to obtain actually higher accuracy than we were able to obtain with these three-dimensional CNNs. So another really interesting piece, right, and an important piece of these Euler characteristic curves and the fact that we're able to understand things through linear regression is that we can sort of get some physical insight from these systems, right? And so what's interesting here, what I'm showing is different simulations for fructose. So fructose is the central molecule, and we're trying to convert that into something that we could turn into, like, let's say, a biopolymer. And on the upper left-hand side, we're seeing, all the different Euler characteristic curves for the different co-solvents that we've dissolved this fructose system in, or this fructose molecule in. And so what we see, right, is that these co-solvents, ACN, DIO, and GVL, these are just names for different chemical formulas, basically. We can see that their topology via the Euler characteristic, as we've denoted here in blue, is really quite similar, right? But when we look at something like THF versus DMSO, right, we see that the topology of these systems is actually very different. And So what we're seeing here, right, is really a connection to the chemistry of the system, right? So the highest reactivity for fructose is given by DMSO, and the lowest reactivity for fructose is given by THF. And so what's interesting here, right, is that when we look at the left-hand side, DMSO is actually going in and interrupting the interactions between different water molecules. So DMSO is sort of coming in and stopping water from forming like these really dense hydrogen bonding networks, right? And so what we see from that is basically that we get water that's more evenly distributed near the central molecule. And so we get these, these smaller pockets inside the simulation. And what we see is, right, is an associated, sort of expansion of the Euler characteristic values, right? Because now we have more connected components, more holes or handles, and then more voids in our system. And we can see that sort of the exact opposite is true for THF, right? So for THF, what we're seeing is a sort of dampening of these Euler characteristic values, which is associated with the formation of these large water clusters in the system. So THF actually causes water to form into these larger globules, right, in these simulations, and prevents water from sort of being separated out. And so the hypothesis here, right, is that DMSO interrupts these water interactions and allows water to more freely interact with that central molecule. Whereas with THF, right, the water is sort of in this sort of condensed phase and maybe isn't as able to interact with fructose because it's busy interacting with itself, essentially. And so I may be a little quick through this presentation, I'm not sure, but basically what I wanted to is that the Euler characteristic and curve and these topological representations of data are providing these empirically, from our experience, robust descriptors for regression, classification, and dimensionality reduction tasks. And so, really the main point that I wanted to show is that a lot of these topological and geometric data analysis methods, I think there's a lot of, there's a tremendous opportunity for applications in areas like chemical engineering, primarily because people from my field aren't too familiar with topology and geometry. And so I think, there's a huge amount of opportunity to sort of integrate these ideas from topology and geometry into the analysis of these really complex engineering data sets that we have tons of, but we don't know what to do with, right? And so with that, I'd just like to acknowledge a lot of my collaborators. So Professor Reed Van Lane from UW-Madison for the molecular simulations, Professor Nick Abbott, who is the expert on the liquid crystal systems, Pavel Dlatko, who some of you may know from the Dioscuri Center for TDA, Spencer Rund, Atharva Kelkar, and Alex Chu, who are all graduate students who are working on molecular simulation analysis. And then my advisor, Victor Zavala, and the NSF MERSEC for funding. And with that, I'd like to show just some references. So this is some of the work, maybe if you guys want to see some of the application areas that we focused on in chemical engineering. So we have these 2 papers here that sort of cover some of this work. And then also for comparison, if you wanted to see these, the convolutional neural network methods that were used previously, and just to show you that, these topological characterizations are actually, able to reduce these more complex models into simpler models. And so with that, I'd be happy to take any questions.
Thank you very much, Alex, for your presentation. It was very interesting. Well, they're telling me that we don't have too much time, so...
Oh, sorry. I didn't realize that. My apologies.
No, that's no problem. No, but thank you very much for everything. It was very interesting.
Thank you.
There is at least one question in the chat, and I have maybe 1 or 2 as well. From Eli Carvonen, have you tried? Are you planning to try to do similar things with real data? I'm not sure. Maybe Eli, if he's here, he can elaborate on what he means. Yes, I see you.
So Eli, so I would say that the liquid crystal systems, for example, those are real experimental data. So those are experiments, and that's actual data. And so, being able to get that information and use the Euler characteristic curve in this application is an example of applying it to real data. Yeah. And just as a side note, the predictions that we were doing for the molecular reaction and the reactivity increase, that's also from real data. So those reactivities are from real data. We're just using simulation data as a surrogate to obtain those different water structures.
Super, thanks. And so if nobody, okay, so if nobody else has a question, I'll ask one of mine. So as I'm looking at all of your pictures, what they remind me of are various simulations of random fields. I was wondering, I mean, this is probably sort of beyond the scope of your experiments and work, but have you tried to make a more formal connection to that area?
Yeah, that's actually one of the goals is to, because with like people like Robert Adler, who I know was your advisor at one point, these ideas of random field theory and their integration through things like the expected Euler characteristic for these systems is something that we're very, very interested in. And in particular, right, so for things like with the liquid crystal system, so like with the liquid crystal system, right, can we connect, maybe the statistics of the random fields that these things are forming to the physics of the liquid crystal system, right? So are there characteristics that we can sort of connect between these systems? And the same with, these water density systems, right? These fluctuations that are on the surface, right? They're doing these very, very advanced sampling methods to obtain these probabilities. But could we look at the structure of the sort of the random field that they're forming to be able to directly analyze that? And so, the idea would be eventually to sort of bypass this idea of linear regression, right? And just directly compute this hydration free energy based on the structure and the statistics of the random fields that these systems are forming.
Great. And a sort of technical point that I'm curious about, but so you're taking kind of filtrations, well, in a certain direction. Right. Does anything change if you reverse the direction?
What we've found is that, there isn't much change in terms of the structures and things like that, because what I'm thinking is happening, right? And maybe you know more about this, is that, if I have, a void that's due to, a high density area, then when I flip it, I just get, a connecting component that's due to the high density area, right? And so, so I think there's the two different filtration directions are sort of complementary in a way. And so we're not finding a large amount of difference. But, a lot of the work that Professor Adler has done is really dealing with sort of the filtration in the opposite way. So that's what I'm sort of trying to shift to that, so that we can start using, these, some of the, like the expected or the characteristic functions to sort of understand these structures.
Great. Okay, well, thanks a lot. I don't have any more questions. Does anyone else? Yep. Thanks again.
Yeah. Thank you guys so much.